A critical principle in understanding radioactivity is radioactive decay and half-life. So let's talk a little bit about the decay process. First of all, when an atom decays, it'll turn from one element to another element. What we've considered up to this point is it will decay and just become that second element and you're done. But more often you have what's called a radioactive decay series, which is that you have one radioactive nucleus which decays into a second nucleus. And that will decay, becoming a third nucleus, which will decay into a fourth nucleus, which decays to a fifth, and so on. This happens very naturally with a whole handful of elements, including thorium-232, uranium-235, and uranium-238. All of these will decay eventually to an isotope of lead. Let's take the uranium-238 example at the bottom. That's what's shown in this graph. If you look at the top left corner of this chart, you'll see uranium-238 as the unstable element that we're dealing with. It then undergoes alpha decay and becomes thorium, which then undergoes beta decay and becomes palladium, undergoes beta decay again and becomes uranium-235, which is quite unstable. Will then undergo alpha decay again and again, going from uranium to thorium to radon, to a whole number of elements. Ending in the very bottom, you have element 82, lead. Pb is lead. And at the very end, you end up with lead-206, which, as we saw at the bottom, at the last point on this slide, uranium-238 naturally decays down to lead-206. So this is a very typical radioactive decay series. Now, how quickly a sample of radioactive nuclei will decay is what we call the half-life. Half-life is the time required for half of a radioactive sample to decay to a different element. So here in this table, there are a number of half-lives labeled here. On the left, you have the isotopes. You have helium-3, or known as tritium, carbon-14. Looking further down, you see uranium-238. Middle column shows their half-life, and right column is the type of decay they usually undergo. For example, uranium-238 has a half-life of 4.5 times 10 to the 9 years. That's 4.5 billion years. And the typical type of decay it undergoes is alpha decay. Now let me give you a quick example of how the half-life, what happens to the isotope dealing with half-life. Let's say that we start off with 1 kilogram of an unstable isotope. And this particular isotope has a half-life of exactly 1 day. Now, what we mean by half-life is half of the material will decay. So after 1 day, we go from 1 kilogram to only having half a kilogram, 500 grams. The other half has already decayed. Is it exactly 500 grams? It's give or take a little bit. Remember that nuclear decay is a random process. So sometimes it'll happen faster, sometimes slower. But on the whole, statistically speaking, half of the material will be left after 1 day in this example, or after the time frame illustrated in this chart. So after 1 day, we've lost half of the isotope. We're down to 500 grams. After 1 more day, half of what's remaining also decays. So half of 500 is 250. We have 250 grams remaining. After another day, half of that remains, going down to 125. And then after that, another half goes down to 62.5, and so on. Every day, the mass of your substance is cut in half. Now, the uranium-238 decay series has a very long variation. This is again the same series we saw in the first slide. undergoing alpha decay to become thorium, then beta decay to palladium, beta decay to uranium-234, so on, all the way until it becomes lead-206 at the end. But what we see is that we have a very wide half-life variation. In other words, the time to go for half-life going from uranium-238 to thorium is 4.5 billion years. But then once it becomes thorium, that half-life is only 24 days. Palladium has a half-life of 1 minute, 1.1 minutes. And then it becomes uranium-234. Notice the half-life there jumps up again and goes up to 2.7 times 10 to the 5th years. That is 270,000 years. And so as you follow along the chart, the half-life changes from element to element, anything from 4.5 billion years down to seconds. You have polonium down near the bottom. Polonium-214 decays to lead-210, has a half-life of 1.5 times 10 to the minus 4th seconds. That's 0.1 milliseconds. Very, very short half-life. So you have a very wide variety of half-lives in this radioactive decay series. Now, how do you measure radiation? Well, there are different methods of measuring radiation. One is the ionization counter. This detects the ions that are produced by radioactive decay. Now, this is probably one of the more common methods. Great example of methods to detect ionization from radioactive decay is the Geiger counter. And if you watch all sorts of sci-fi movies or any type of movie really where they have to deal with nuclear radiation, they always pull out the Geiger counter. This is the principle it uses to detect radiation, the number of ions produced by radioactive decay. You also have what's called the scintillation counter, which relies, of course, on the flashes of light that are produced as radiation strikes phosphorescent glass. Very similar to a cathode ray tube. You shoot electrons at the screen, it'll glow. Very similarly, you have a phosphorescent surface, a glass jar, if you will. As radioactive decay occurs, some of the particles, like alpha particles, will hit the screen and will glow. So the scintillation counter just counts the number of glows and will be able to tell you how much radiation is in the area based on scintillation. Now there are lots of units. I'm just going to go through this very quickly. Lots of units are used to measure radiation. One of the most common units is the becquerel. That is the International System Unit for measuring radiation. However, we often see other units more commonly here, especially in the United States, such as sieverts and curies or rems. Rems and millirems are very, very commonly used. Now, the element or the unit used will often vary depending on how they are used. For example, when we're talking about human exposure to radiation, we usually use the unit rem. An SI unit, International System Unit, millisievert is very commonly used. Amount of radiation absorbed, you could use the unit of grays, and so on. Now, the amount of radiation absorbed is related to the effects on the organism, the health hazards. If you look at the bottom part of this chart, that talks about different human effects on organisms based on the dosage. And you can find this table in your textbook. Now, How much radiation are we exposed to? Well, honestly, we are always exposed to radiation, to radioactivity. It is happening all around us day and night. Thankfully, not in large amounts. Normally, we get somewhere between 100 and 500 millirems per year. That's not much. The variation depends on where you are. For instance, here in Florida, we're probably fairly low, somewhere around 200 or so. Whereas if you go to a city such as Denver, they're higher up in the mountains, there are more minerals around them, the natural radioactivity is happening a lot more. They'll be closer to the 500 millirems per year. So the amount of exposure to radiation we have depends on location, depends on time of year, depends on cycles of the Earth and the Sun, so on. And also, there are lots of sources for this natural radioactivity. Cosmic rays from space, residual radioactivity from the formation of the Earth itself, and so on. Not to mention other sources that we expose ourselves to. Medical x-rays, television, so on. They all expose us to radiation. As long as we're in this range, the 100 to 500, we are safe. There aren't really any prolonged disruptions to the human body. If you get more than that, you may see consequences such as DNA disruption or free radical production, which is spontaneous breakdown of cells and organisms, can lead to things such as cancer. Now, how much can the human body withstand? Well, there are a couple of different models depending on who you talk to, the study that's done, and what you're evaluating. One is the threshold exposure model. That's the figure on the left here. Basically, the amount of biological damage that the body can withstand is relatively low and constant, even with increasing radiation exposure up to a certain point. At that point, or your threshold of damaging dose, you start undergoing more biological damage. Now, contrast that with the linear exposure model, which is the figure on the right, which basically says any amount of radiation is going to damage you, any more radiation is going to damage you more. So the more radiation, the more damage. Straight up one-to-one relationship. Now, both models are accepted, again, depending on the type of study and the type of biological damage you are addressing.